The universe is not a silent void. It is a graveyard of violent histories, a dark theater where the laws of physics occasionally create monsters. We often look to the stars with a sense of wonder, searching for life, for connection, for meaning. But what if the darkness stares back? What if a cosmic predator, born from the chaotic screams of the Big Bang itself, is currently racing toward us at the speed of light? We are speaking of a black hole, an object of infinite density and zero volume, a tear in the fabric of reality that refuses to let light escape. In this terrifying thought experiment, we are not merely observing these anomalies from the safety of a telescope. We are placing Earth directly in their crosshairs. To understand the gravity of this situation, we must first look at the taxonomy of these celestial devourers. Most of the black holes we identify are stellar mass entities, the corpses of massive stars at least 8 times heavier than our Sun that have collapsed under their own weight. The nearest known example, Gaia BH1, lurks just 1,560 light-years away. It is a dormant beast, 10 times the mass of our Sun, with an event horizon, the point of no return, spanning only 37 miles. But there is another class of black hole, one that exists only in the theoretical margins of cosmology, yet holds a terrifying potential for destruction. We must rewind the cosmic clock to the very beginning, 13.8 billion years ago. In the fraction of a second following the Big Bang, the universe was a hot, dense soup of fundamental particles. It was a time of violent asymmetry. Before the first stars ignited, before galaxies spun into existence, density fluctuations in this primordial plasma may have been extreme enough to collapse pockets of matter directly into singularities. Scientists call these primordial black holes. They are the ghosts of the universe's infancy. While we have never directly observed one, largely because they are either too small to detect or have long since evaporated via Hawking radiation, the mathematics suggests they could still be out there. Some might be as small as a single proton, yet weigh as much as a mountain. But for our scenario, let us imagine a primordial black hole that has survived the eons, drifting silently through the interstellar void. We will assign it a specific mass, the exact mass of the Earth. This creates a fascinating and horrifying paradox. A black hole with the mass of our planet would not look like a planet. Because gravity is a function of density, crushing the Earth into a singularity would shrink it down to a Schwarzschild radius of less than 1 inch. Imagine a black marble, just 2 centimeters wide, possessing the gravitational authority of our entire world. It is a coin-sized apocalypse. Now, accelerate this object to the speed of light, approximately 186,000 miles per second, and aim it at the heart of our solar system. Because of its diminutive size, you would not see it coming. There would be no shadow crossing the stars, no warning blip on a radar screen. It absorbs light perfectly. It is invisible, a phantom bullet moving so fast that our sensory instruments would fail to register its approach until the moment of interaction. If this object were to fly by Earth, missing us by a narrow margin, the consequences would still be cataclysmic. Gravity acts instantly. As the black hole screams past, it would exert a sudden, violent tug on our planet. This is where the horror of tidal forces comes into play. Gravity weakens with distance, meaning the side of Earth facing the black hole would be pulled significantly harder than the side facing away. The planet would be stretched, distorted into an ovoid shape in a matter of milliseconds. The crust, unable to deform rapidly enough to match this gravitational shearing, would shatter. We are not talking about localized tremors. We are visualizing a global fracture. Every fault line on Earth would slip simultaneously. Supervolcanoes, long dormant, would be squeezed like pressurized bladders, erupting in unison. The oceans, dragged by this invisible hand, would rise in mega-tsunamis that would scrub entire continents clean of civilization. But the physical destruction of the surface is only the immediate symptom. The celestial mechanics of our home would be rewritten. A flyby of this magnitude would transfer orbital energy to Earth. Depending on the trajectory, our planet could be yanked out of its habitable groove. We might be pulled inward, closer to the sun, where the atmosphere would boil and the oceans would evaporate into a runaway greenhouse hellscape. Conversely, we could be flung outward, toward the freezing orbit of Mars. As we drift away from our star, the global temperature would plummet, turning Earth into a snowball, a frozen tomb drifting through the dark. However, the true nightmare begins if this object does not miss. What if the trajectory is perfect? What if this 2-centimeter singularity strikes the center of the Earth? At the speed of light, the impact would be over in 0.04 seconds. It would be akin to shooting a rifle bullet through a sphere of gelatin, but on a planetary scale. The black hole would pierce the crust, the mantle, and the iron core without slowing down. It would create a needle-thin tunnel through the planet, a vacuum tube of absolute destruction. But the size of the hole is irrelevant. It is the gravity that kills. As the black hole burrows through the Earth's interior, it pulls matter toward it from all directions. The rock and metal surrounding its path would be instantly spaghettified, stretched into long, thin strands of superheated plasma before being consumed or flung outward at relativistic speeds. This would generate a shockwave of unimaginable power. The entry and exit wounds on the Earth's surface would not look like small punctures. They would be explosive craters erupting with the energy of billions of nuclear warheads as the kinetic energy of the displaced matter converts into heat. Inside the Earth, the core would be disrupted. The delicate dynamo that generates our magnetic field could be destabilized. Seismic waves of a magnitude never before seen, let's call them planetary resonance events, would ripple through the globe. The ground beneath your feet would liquefy. The structural integrity of the planet itself would be compromised. It would be the ultimate betrayal of physics, the ground, the very symbol of solidity, turning into a fluid, chaotic mess. For those of us on the surface, the experience would be confusing and terrifyingly brief. One moment, the sky is clear. The next, the ground lurches violently as the gravitational center of the planet momentarily shifts toward the passing intruder. You would feel lighter, then heavier, then thrown sideways as the vector of gravity gyrates wildly. Buildings would not just collapse, they would be torn apart at the molecular level by the shearing forces. And then, silence. The black hole would exit the other side of the planet, continuing its journey into the cosmos as if nothing happened. It leaves behind a wounded world, a planet bleeding magma into space, its orbit shattered, its surface sterilized. The indifference of the universe is perhaps the most chilling aspect of this scenario. The black hole bears no malice. It is simply a mathematical inevitability, a dense pocket of curvature following a geodesic line through spacetime. We were just in the way. Yet this Earth-mass black hole is merely a toy in the grand arsenal of the cosmos. It is a microscopic anomaly compared to the true giants that lurk in the deep dark. As we assess the wreckage of our hypothetical Earth, we must realize that size, in the context of black holes, is a deceptive metric. We have survived the needle, the coin-sized assassin. But what happens when the intruder is not a remnant of the Big Bang, but a corpse of a star? What happens when the event horizon is not the size of a coin, but the size of a city? The universe has larger ammunition, and it is reloading. The next visitor is not a theoretical primordial ghost, but a stellar mass reality, a crushing void 10 times the mass of our sun. The physics are about to change from a surgical strike to a bludgeoning trauma. Prepare yourself, for the scale of destruction is about to increase exponentially. In the grand theater of cosmic horrors, the primordial black hole was merely a prelude, a microscopic assassin. We now turn our gaze to a far more common, yet infinitely more brutal executioner, the stellar mass black hole. This is the final tomb of a star that once burned brighter than our sun. It is a ghost of stellar majesty, collapsed into a singularity where time and space go to die. For this scenario, we are summoning a beast weighing 10 solar masses. To visualize this, imagine crushing 10 of our suns into a sphere the size of a metropolitan city, specifically an event horizon spanning just 37 miles across. It is smaller than the drive across Rhode Island, yet it anchors the gravitational authority to shred entire planetary systems. Let us place this object on the same trajectory as its predecessor, a relativistic approach at the speed of light. But this time, the warning signs would not be so subtle. The mass of 10 suns does not move through the solar system unnoticed. It commands obedience from everything it passes. From the moment this dark intruder pierces the Oort cloud and enters the Kuiper belt, the delicate gravitational balance of our neighborhood is shattered. We would have approximately 5.5 hours before the end of the world. In the cold, dark outer reaches, the orbits of dwarf planets like Pluto and Eris would be instantly scrambled, flung into deep space, or pulled into chaotic, elliptical death spirals. As the black hole races inward, astronomers would witness the impossible, the gas giant Jupiter, the king of our planets, trembling. If the black hole passed near Jupiter, we wouldn't see gas spiraling into a glowing accretion disk. The intruder is moving too fast for that. Instead, we would see a gravitational bully, simply shoving the giant aside. Jupiter's massive moon system would be thrown into disarray, potentially stripping the planet of its satellites entirely. The gravitational perturbation would be so severe that Jupiter's orbit would warp, sending ripples of instability toward the inner solar system. 30 minutes later, Mars would face a similar fate. The red planet wouldn't be swallowed, it would be unmoored. The black hole's gravity would snap the invisible tether holding Mars to the Sun, flinging it into the void like a stone from a sling. On Earth, the panic would be absolute. But before the ground shook, the sky would break. As the black hole approached, invisible to the naked eye, its gravity would act as a lens, bending the light of the stars behind it. You would see a swirling, sickening distortion in the heavens, a funhouse mirror effect, where constellations twist and smear around a central point of absolute darkness. This is gravitational lensing, the universe's way of visualizing the curvature of spacetime. It would be beautiful if it weren't the harbinger of extinction. Let us first consider the lucky scenario, a near miss. The black hole doesn't hit us, but passes within a few thousand miles. Even without contact, the proximity of 10 solar masses would subject Earth to tidal forces beyond comprehension. We are accustomed to the moon's gentle tug creating ocean tides. This black hole would create tides of rock. The Earth is not a rigid solid, it is elastic. As the singularity screams past, the side of the Earth facing it would be pulled with exponentially more force than the far side. The planet would stretch into an oblong spheroid. The crust would not just crack, it would liquefy. Continents would be torn asunder as the ground beneath them stretched like taffy. This is not an earthquake. This is a starquake on a planetary scale. The friction generated by this flexing would heat the Earth's interior instantly. Magma would erupt from every fissure, turning the surface into a global ocean of fire. The atmosphere, stripped away by the passing gravitational wake, would vanish into space, leaving the boiling oceans to sublimate into a vacuum. We would survive the flyby, only to find ourselves on a sterilized, molten rock, likely ejected from the solar system entirely, destined to freeze in the interstellar dark. But we promised you a collision. We promised to send this stellar mass monster directly through the heart of our world. If a black hole of 10 solar masses, moving at 186,000 miles per second, were to strike Earth, the concept of impact fails to capture the physics involved. It is not a collision of matter, it is a collision of math. The event would last 0.04 seconds. In that fraction of a heartbeat, the black hole would punch through the crust, the mantle, the outer core, and the inner core and exit the other side. But unlike the coin-sized primordial hole, this object has an event horizon 37 miles wide. It is wider than the Earth's crust is thick. It would not leave a needle-thin tunnel, it would core the planet like an apple. As the event horizon makes contact, the matter in its path doesn't just fall in, it is spaghettified. The gravity is so intense that the pull on a rock or a person is millions of times stronger at the bottom than at the top. Matter is stretched into long, monomolecular strings of plasma before vanishing into the void. The Earth would not just be pierced, it would be pulled inward. The moment the black hole touches the atmosphere, a cylinder of Earth's material roughly 40 miles wide is instantly deleted from our reality, added to the mass of the black hole. But the destruction extends far beyond the tunnel. As the black hole traverses the planet's interior, its gravity drags the surrounding mantle and core inward at relativistic speeds. It creates a supersonic implosion following in its wake. The Earth momentarily collapses in on itself, drawn toward the moving center of gravity, only to rebound violently once the intruder exits. The shock wave generated by this passage is incalculable. We are talking about energy release equivalent to a supernova occurring inside the planet. The friction of the black hole passing through the core would superheat the entire globe in milliseconds. The oceans would flash boil into steam instantly. The atmosphere would ignite into plasma. The crust would be blown outward into space, not as rocks, but as vapor. From the perspective of a distant observer on the moon, Earth would simply cease to be a planet. One moment, a blue marble. The next, a blinding flash of light as the kinetic energy of the impact converts into heat. Then, a rapidly expanding cloud of debris. There would be no rubble to stand on, no ruins to explore. The planet would be atomized, reduced to a smoldering nebula of gas and dust. And the black hole? It would not slow down. It would not notice. It would absorb a tiny fraction of Earth's mass, a rounding error in its grand equation, and continue its journey across the galaxy, leaving behind only a gravitational echo and a cloud of expanding plasma where a civilization used to be. This is the terrifying reality of stellar mass black holes. They are the sledgehammers of the universe, possessing enough mass to disrupt the celestial mechanics of an entire system, and enough density to erase a planet without pausing. Yet, in the taxonomy of the dark, these are still considered small. They are the common foot soldiers of the galactic void. There exists a rarer, more elusive class of monster, a missing link in the evolution of darkness. Astronomers have hunted them for decades, finding only whispers in the data. These are the intermediate mass black holes, the middle children of cosmic destruction. They are not formed from the death of a single star, but perhaps from the cannibalistic merger of thousands. If a stellar mass black hole is a sledgehammer, an intermediate mass black hole is a wrecking ball the size of a moon. And if one of these were to set its sights on Earth, the physics of our destruction would shift from a violent puncture to a total agonizing consumption. The meal is about to get larger, and the table manners of the universe are about to get much worse. The universe is vast, but it is not empty. Between the blinding deaths of stars and the swirling hearts of galaxies lies a shadowy middle ground, a realm inhabited by the elusive and terrifying intermediate mass black holes. While stellar mass black holes are the scattered shrapnel of the cosmos, and supermassive giants are the anchors of galactic civilization, these intermediate monsters are the missing links of astrophysics. They are rare, difficult to detect, and possess a mass ranging from a few hundred to a few 100,000 times that of our Sun. They are the result of a cosmic gluttony, formed perhaps by the runaway merger of smaller black holes in the dense clusters of the early universe. They are not just dead stars, they are graveyards of stars. In our escalating nightmare, we now summon one of these intermediate beasts. Let us assign it a mass of 1,000 suns. To visualize this, we must discard the image of the coin-sized killer or the city-sized bullet. A black hole with the mass of 1,000 suns has a Schwarzschild radius, the radius of the event horizon, of approximately 1,800 miles. That gives it a diameter of roughly 3,600 miles. This is an object of absolute darkness, roughly the size of the planet Mars, or about half the size of Earth itself. This is no longer a puncture wound. This is a mouth. If such an object were to enter our solar system, the gravitational hierarchy would be instantly overthrown. The Sun would no longer be the undisputed master of our celestial neighborhood. The planets would find themselves caught in a chaotic tug-of-war between their parent star and this intruder. But we are not here to discuss orbital mechanics. We are here to witness the end of the world. Let us imagine this Mars-sized sphere of nothingness traveling at the speed of light on a direct collision course with Earth. As it approaches, the visual distortion would be psychedelic. The black hole would appear as a hole in reality, surrounded by a thin, glowing ring known as the photon sphere, a region where gravity is so strong that light itself is trapped in orbit. Behind it, the entire star field would be warped into a chaotic smear. But unlike the smaller black holes, this object is large enough to be seen with the naked eye as a growing disk of void, blotting out the constellations one by one. When an object of this magnitude strikes the Earth, we enter the realm of a tidal disruption event, a phenomenon usually reserved for stars wandering too close to galactic centers. But here, the victim is a rocky planet. As the black hole closes the final distance, Earth enters the Roche limit, the invisible boundary where the tidal forces of the black hole overcome the self-gravity holding the planet together. Before the event horizon even touches our atmosphere, the Earth would begin to disintegrate. We are not talking about earthquakes or tsunamis anymore. We are talking about the structural failure of the entire globe. The side of the Earth facing the black hole would simply lift off. Oceans, crust, and mantle would be stripped away, spiraling upward into the vacuum to meet the oncoming void. Then the collision. Because the black hole is roughly half the size of Earth, it wouldn't drill a hole. It would consume the planet from the inside out. The impact would be silent, for sound cannot travel in a vacuum, and the atmosphere would be the first thing to vanish. The black hole would crash into the Earth's hemisphere, swallowing continents whole. North America, the Pacific Ocean, and parts of Asia would disappear into the event horizon in a microsecond. They would not be destroyed in the conventional sense. They would simply cease to exist in our observable universe. For the briefest moment, as the black hole plunges deep into the planetary core, the Earth would look like a hollowed-out shell, a fruit being devoured by a worm. But the gravity of 1,000 suns is relentless. The remaining shell of the planet, the side facing away from the impact, would instantly collapse inward to fill the void. The planet would turn itself inside out. The crust would fold, buckle, and rush toward the center at a significant fraction of the speed of light. This is where the horror of spaghettification becomes absolute. In the intense gravity near the horizon, the difference in pull between your head and your feet is enough to snap the molecular bonds of your body. But on a planetary scale, this stretching applies to mountains, to tectonic plates, to the iron core. The Earth would be drawn into a long, superheated stream of plasma spiraling into the black hole's maw. The friction from this rapid accretion would generate a burst of X-rays and gamma rays bright enough to be seen across the galaxy, a final, screaming death knell of our world. But there is a stranger, more philosophical horror awaiting us at the threshold of the event horizon. It involves the distortion of time itself. According to Einstein's theory of general relativity, gravity dilates time. The stronger the gravitational field, the slower time moves relative to a distant observer. If you were watching this catastrophe from a safe distance, say from the orbit of Saturn, you might see something impossible. As the remnants of Earth approach the event horizon, they would appear to slow down. The light reflecting off the crumbling cities would shift to the red end of the spectrum, growing dimmer and redder as the photons struggle to climb out of the gravity well. Ideally, you would see the image of Earth frozen in time, plastered against the surface of the black hole, fading into eternal darkness. It is a ghostly afterimage, a cosmic photograph of the destruction preserved forever on the edge of oblivion. However, for us on Earth, there is no such pause. There is no slow-motion finale. In our frame of reference, the end is instantaneous. We cross the threshold without realizing it. One moment, we are part of the physical universe. The next, we are information encoded on the singularity. The laws of physics as we know them break down. We become part of the mass, the charge, and the spin of the black hole. Our history, our biology, our art, and our wars are compressed into a point of infinite density. Unlike the stellar mass black hole, which left behind a cloud of vaporized debris, the intermediate mass black hole leaves nothing. It is a clean eater. It creates a vacuum where a planet used to be. The space Earth occupied is now empty, save for the dark sphere rushing onward. The Moon, suddenly bereft of its partner, would be flung tangentially into the dark, a lonely orphan wandering the solar system. The terrifying efficiency of this destruction highlights the fragility of matter against the curvature of spacetime. We tend to think of the ground as solid, of the Earth as permanent. But in the presence of 1,000 solar masses, matter is fluid. It is transient. We are merely dust waiting to be collected. And yet, even this cataclysm pales in comparison to what lies at the heart of the galaxy. We have faced the needle, the bullet, and the wrecking ball. But the universe has one final terror in its arsenal. It is the king of monsters, the anchor of galaxies, a beast so large that it defies human comprehension. We are moving from the intermediate to the supermassive. We are moving from the destruction of a planet to the disruption of a star system. The apex predator is coming, and it does not just want the Earth, it wants everything. We have witnessed the surgical precision of the primordial singularity. We have endured the brutal puncture of the stellar mass ghost. We have watched our world be consumed by the intermediate void. But these were merely local tragedies, planetary executions. Now we face a cosmic extinction event. We are summoning the apex predator. Meet Phoenix A, the most massive black hole ever discovered by humanity. To call Phoenix A black hole is a linguistic failure. It is a gravitational abyss of such magnitude that it defies human visualization. It possesses the mass of 100 billion suns. Its event horizon stretches for 370 billion miles. To put that in perspective, this single object is 100 times wider than the distance between the Sun and Pluto. It is not merely a hole in the universe, it is a universe unto itself, a dark god sitting at the center of the Phoenix cluster, 5.8 billion light-years away. It could swallow our entire solar system without registering a significant increase in mass. But in our final, terrifying thought experiment, we bring this titan to our doorstep. We accelerate this galactic anchor to the speed of light and aim it directly at our sun. The arrival of Phoenix A would not be a sudden event. Its gravity is so immense that it would be felt long before the object itself arrived. As it approaches the outer edges of our solar system, the fabric of spacetime would begin to warp violently. This is not just gravitational lensing, this is gravitational dominance. The entire sky would change. The stars would not just smear, they would be dragged across the heavens as if the universe itself were rotating around a new, terrible axis. The first casualties would be the outer giants. Neptune and Uranus would not merely be disturbed, they would be stripped from their orbits instantly. The gravitational pull of Phoenix A is so overwhelming that the sun's hold on its planets would be rendered negligible. Our solar system, a clockwork mechanism that has ticked for 4.5 billion years, would be dismantled in minutes. On Earth, the end would begin with the tides. But these are not the tides of water or rock we spoke of before. These are tides of atmosphere and light. As the monster approaches, the sky would darken, not because of clouds, but because the light from the sun would be bent away from us, sucked into the approaching maw. Daylight would fail, not from an eclipse, but because the photons themselves are being conscripted by a stronger master. Then the oceans would rise. Not in waves, but in a single global bulge, drawn upward by the inescapable attraction of 100 billion solar masses. As Phoenix A tears past the orbit of Jupiter, moving at the speed of light, the effect on Earth would be paradoxical. For a few fleeting seconds, gravity would seem to disappear. Everything not anchored to the bedrock, cars, people, buildings, the ocean itself, would lift off the ground. We would experience a moment of suspended animation, a terrifying weightlessness, as the Earth falls faster than we do toward the approaching event horizon. Then, the chaos. The sun, our life-giver, would be the first to die. It would not be swallowed whole, it would be shredded. The tidal forces of Phoenix A would stretch our star into a long, glowing ribbon of plasma, a streamer of nuclear fire spiraling into the dark. The light of our sun would be extinguished, replaced by the blinding accretion disk of the black hole, a swirling storm of superheated matter shining with the brilliance of 1 trillion stars. Earth would be nothing more than a speck of dust in this storm. As Phoenix A screams past at light speed, the gravitational shockwave would shatter the planet. We wouldn't even have the dignity of being spaghettified into the hole. The tidal forces would simply pulverize the Earth into a cloud of debris. The crust would explode outward. The core would detonate. In the span of 0.04 seconds, the Earth, the Moon, and every planet in the inner solar system would be reduced to a chaotic spray of atoms. But let us imagine, for the sake of the narrative, a gentler flyby. Let us assume Phoenix A passes just far enough away that Earth is not instantly vaporized, but merely evicted. As the black hole dominates the local gravity, Earth would be flung out of its orbit with unimaginable velocity. We would be ejected from the solar system at a significant fraction of the speed of light. The sun would recede into the distance, a dying ember in the rearview mirror. We would become a rogue planet, a lonely wanderer in the interstellar deep freeze. The consequences for life would be immediate and total. Without the sun, temperatures would plummet within days. The oceans would freeze over, creating a global ice sheet miles thick. The atmosphere, no longer heated by solar radiation, would eventually condense and snow out, oxygen and nitrogen raining down as liquid, then freezing into solid ice. Earth would become a silent, frozen mausoleum, drifting through the void for eternity. Civilization would collapse in hours. The power grids would fail. The food chains would shatter. Humanity might survive for a short while in deep underground bunkers, powered by geothermal energy, huddled around the dying warmth of the planet's core. But eventually, the internal heat would fade. The darkness would win. And Phoenix A? It would continue its journey, indifferent to the destruction of a minor star system. It has consumed galaxies. It has merged with other supermassive black holes. The consumption of our sun and its planets adds nothing to its mass, nothing to its legacy. We are less than a rounding error. This journey through the scales of black holes, from the primordial atom to the galactic titan, reveals a humbling truth about our existence. We live in a fragile bubble of stability, protected by the vast distances of space. Gravity is the sculptor of the universe, but it is also its destroyer. It builds stars. It holds planets in orbit, but when concentrated into a singularity, it becomes the ultimate eraser.
We are lucky. The nearest black hole is thousands of light years away. The monsters we have conjured today exist only in our mathematics and our nightmares. But they are out there, silent, waiting, feasting on the light of the cosmos. So the next time you look up at the night sky, at the peaceful tapestry of stars, remember what lies in the spaces between them. Remember the needle, the bullet, the mouth, and the abyss. The universe is beautiful, yes, but it is also a machine of infinite violence, and we are just passing through.